Hi everyone, welcome back to Lulumath. This video is on transformations of functions. This is the third video, and we're going to talk about vertical stretches, compressions, and vertical reflections in this video. And you'll need to have an understanding of parent functions, and there are two videos at lulumath.com as well as the Lulumath YouTube channel if you need a refresher on parent functions. So we're going to consider some parent functions, including quadratic, square root, absolute value, reciprocal, and exponential functions. And we're going to determine the effect that a has on y equals a multiplied by f of x for a equals 2, 1/3, -4, and this should say -1/5. So for this video, we're going to start by taking a look at absolute value functions. And our parent function for an absolute value function is f of x is equal to the absolute value of x. This is the most basic form of an absolute value function. Now, we are going to look at y equals a times f of x. And if you notice here, this f of x is our output. And this is saying that this is going to give us our new output. And it's going to be equal to a multiplied by our old output. And one important thing is that our input does not change. And because we are changing our old output to get a new output, that's why we are going to be talking about vertical stretches, compressions, and reflections. But let's see what happens first. So in the first equation that we have here, it's y equals 2 times f of x. So if f of x is the absolute value of x, then my equation is going to be 2 multiplied by what f of x is, which is the absolute value of x. Our next one is y equals 1/3 f of x. So my equation is going to say y equals 1/3, well, f of x is the absolute value of x. Our next one is y equals -4 multiplied by f of x. So the equation is going to say y equals -4 multiplied by the absolute value of x. And then our last one is y equals -1/5 f of x. Go ahead and write down what you think this equation should say. Did you get y equals -1/5 multiplied by the absolute value of x? If you notice, none of these values, the 2, the 1/3, the -4, the -1/5, none of these values are affecting our input. Our input is still just the x. So let's go ahead and use the graphing technology. We'll use Desmos to see what this is going to look like. So our parent graph is f of x is equal to the absolute value of x, and this is the general shape that we get when we have an absolute value graph. This is the simplest graph that we could have. And I could either type in y equals, for my first graph, 2 multiplied by the absolute value of x, or I could just type in y equals 2 times f of x. And I'm going to do y equals 2 times f of x because if I change my parent graph to like x squared, for example, my new graph will change with it. So I will type in the remaining equations using f of x. So I'm going to turn on my first graph, y equals 2 times f of x. My graph hasn't shifted, it hasn't translated, it hasn't gone up, down, left, or right, but it does appear to be narrower or thinner. And when I turn on y equals 1/3 f of x, same thing, it hasn't translated, it hasn't shifted, but it appears to be wider. Well, why is this? Why is this happening? So looking at our graph right here, we can see that the black graph is our parent graph. And for our first point that we have here, this is at 3 right here. It has a height of 3. For this point right here, this point came from y equals 2 times f of x. So I'm going to take my output, which was 3, and twice as big as 3 is now 6. So it's twice as big. Let's see if it's the same over here. So this height right here is 2, and now it has a new height of 4 because 2 times 2 is 4. It's twice as big. Now let's see what happened with 1/3 times f of x. So again, this has a height of 3. This is the original graph right here. And if you see here, this has a height of 1, and 1 is 1/3 of 3. 1/3 times 3 is equal to 1. If you see here, this has a height of 1, but the 1/3 times f of x only has a height of 1/3. You're cutting it into thirds. It's getting shorter. So for y equals 2 times f of x, this graph right here, my graph is getting stretched vertically. It's getting taller. It's like you have a piece of gum and you're pulling it up. And for y equals 1/3 times f of x, my graph is getting pushed down. You're smushing it down. And because it's only my y values that are being affected, it's being stretched vertically. And here, it's getting pushed down. We call this a compression. It is compressing the graph. And again, it's vertically compressing it. Okay, so now let's see what happens when we have an a value that is negative. So here we've got y equals -4 times f of x. If you see here, our graph is actually narrower, just like when a was 2, when it was 2 times f of x. But our graph no longer opens up, but now it opens down. It is reflected over the x-axis. It has flipped over the x-axis. And let's see what happens with y equals -1/5 f of x. Same thing, it is reflected over the x-axis, but this time it is wider. So let's put in -4 times y because that's what this equation says. Y equals -4 times f of x. So if you see, I would take all of my y values and multiply them by -4. So instead of -3 right here, we now have -3, -12. So it not only is it taller because it's been stretched, but it is now negative, which takes it from above the x-axis to below the x-axis, which is why it is a reflection in the x-axis. All of my y values have become negative or have stayed at 0. This point stays at 0, but the remaining y values have all become negative, and they've also become taller. They're stretched. It's like a piece of gum that's being stretched down. Now let's see what happens if our a value is -1/5. So I'm going to put a negative in front right here, and we'll change this denominator to a 5. So if you see here, when our a value is -1/5, all of our corresponding y values are now negative, except again at 0, but they're smaller, they're shorter. So instead of -3, +3, we're now at -3, -0.6. It's smaller, it's gotten compressed. But because all of my y values, except for 0, have become negative, it is now below the x-axis, which again tells us that we have a reflection in the x-axis. How do we use this information to help us out when we get into more complicated transformations of graphs? Well, we need to understand how to create our tables of values. Because our parent function is the absolute value of x, when I fill in my general table of values, we know that all of these values will all be positive except for 0, will stay 0. And because my input does not change, this column for my x values stays the same. So when I do my graphs, I keep my x values the same, and then I find out what my corresponding y values will be. For y equals 2 times f of x, I am going to take all of my f of x values and I'm going to multiply them by 2. 3 times 2 is 6, 2 times 2 is 4, 1 times 2 is 2, 0 times 2 is 0, so on and so forth. For y equals 1/3 f of x, I will take each one of my x values here and multiply them by 1/3. So 3 times 1/3 is 1. 2 times 1/3 is 2/3. I'm pretty much just dividing by 3. 1 multiplied by 1/3 is 1/3, so on and so forth. If I wanted to graph out this function here, I would take these x values and these y values, and I would graph them out. Now, for y equals -4 times the absolute value of x, or y equals -4 f of x, I would just take all of my y values that I see here and multiply them by -4. So -12, -8, -4, 0, 4, 8, 12, so on and so forth. And for y equals -1/5 f of x, I will just take each one of my y values here and I would multiply them all by -1/5 or divide by -5. So I would get -3/5, -2/5, -1/5, 0, so on and so forth. So as you can see, negative, negative. So as you can see, my y values become negative, and I apologize, these should also be negatives here as well. My y values become negative, so there's the reflection. And then in some situations, my y values become larger. So this is where I would get my stretch. And in some situations, my y values would become smaller, and this is where I would get my compressions. Now for quadratic functions, our parent function would be f of x equals x squared. So for my first equation here, y equals 2 times f of x, I'm just going to take my f of x, which is x squared, and I'm going to multiply it by 2. So this would be y equals 2x squared. For this next one, I would take my f of x, which is x squared, and I would multiply it by 1/3. So y equals 1/3 x squared. For the next one, it would be y equals negative 4 times f of x. So I would multiply x squared by negative 4. Try the last one on your own and see how you do. You should get y equals negative 1/5 x squared. Now, because in this one, all my y values are getting multiplied by 2, we can say that our graph is being stretched vertically. And in fact, we would say it's stretched vertically with a scale factor of 2. And then here, because all of our outputs are being multiplied by 1/3 or divided by 3, this graph is vertically compressed. And we'll say that the scale factor is 1/3. So here we have to be careful about our language, because when we say the scale factor is 1/3, that implies a compression. Sometimes we'll say it's a compression of 3 because it becomes a third as big. So the compressed kind of implies this 1/over aspect right here. But the scale factor is 1/3. We multiply our y values by 1/3. Let's double check this to make sure that this is right. So here, again, the beauty of Desmos, we just have to change our parent graph to y equals x squared. We have our parabola here. Y equals 2x squared. We can see it looks skinnier. And the reason why it looks skinnier is because it's getting stretched up. Imagine a piece of gum that's getting stretched vertically. It looks like it's getting skinnier, but that's because it's getting pulled up. And then y equals 1/3 x squared is getting pushed down, which is making it look a little bit wider. Now for our next one, because of this 4 right here, our graph is going to get taller, which means that the graph is vertically stretched again. And our scale factor is 4. But what is that negative telling us? Well, all of our y values now become negative. So they were originally above the x-axis, because when we square any number, they're always positive, and then they will be below the x-axis. So because the y values become negative, it is reflected in the x-axis. And then this one right here, the negative 1/5, it is vertically compressed because it's getting shorter. And this time our scale factor is 1/5. But because of this negative sign, all of our y values are flipping over the x-axis. Let's see if that is true here. So y equals negative 4 f of x. It is reflected in the x-axis and it is stretched vertically. And y equals negative 1/5 f of x is reflected in the x-axis and it is compressed. It looks wider. It appears wider because it is shorter. And then for our exponential function, our parent function would be f of x equals 2 to the power of x, but we can use any base that we want. I just happen to use 2 as my base, but it doesn't really matter. But if I use 2 as my base, let's go ahead and color code these. So for our red one, we will take this 2 to the power of x, and we will multiply it by 2. So it's 2 times 2 to the power of x. Our blue graph, we're multiplying 2 to the power of x by 1/3. So it's 1/3 times 2 to the power of x. Now be careful. This does not become y equals 4 to the power of x because only 2 is being raised to the power of x. This 2 is not. And this one does not become y equals 2/3 to the power of x, just because we would multiply 1/3 by 2. Because whenever we do order of operations, we always do our exponents first, and the exponent is changing. It's our variable. So then we can't combine this 2 with this 1/3. We can't multiply them together because we have to do the exponent first. For the next one, Our a value is -4, so we're going to do -4 multiplied by 2 to the power of x. And then for our last one, we would do y equals -1/5 multiplied by 2 to the power of x. Now, everything that we set up here is going to be true about our exponential function. The only difference is just our parent function is different. The red graph is still going to be vertically stretched with a scale factor of 2. This blue graph right here is still going to be vertically compressed with a scale factor of 1/3, so on and so forth. So let's double check on Desmos and see if that's the case. So we can change our parent graph to 2 to the power of x. And you can see when the a value is 2, our graph was stretched vertically. When the a value was 1/3, our graph was compressed vertically. When the a value was -4, our graph was stretched vertically and it was reflected in the x-axis. And when the a value was -1/5, our graph was compressed vertically and reflected in the x-axis. Now, this works for any base. So instead of 2 to the power of x, I'm just going to say b to the power of x. And no matter what we use for our b value right here, all of these transformations apply. Doesn't change the fact that the graphs are compressed or stretched vertically or reflected in the x-axis. And even when our base is a decimal or a fraction, even though our graph looks slightly different, each one of these is still a vertical stretch, a vertical compression, a reflection in the x-axis, a reflection in the x-axis, and a vertical compression. So let's summarize what we have learned here. So if we have y equals a times f of x, a will determine a vertical stretch or a compression and whether or not your graph is reflected in the x-axis. And the sign has nothing to do with the stretches or the compressions. The sign will only tell us whether it's reflected in the x-axis or not. So because of that, when we're looking at whether it's stretched or compressed, we don't worry about the sign, so we just take the absolute value of a. And if the absolute value of a is greater than 1, then we have a vertical stretch. And our graph appears to be narrower because it is getting stretched up. If a is between 0 and 1, the absolute value of a, because again, the sign doesn't matter for our stretches and compressions, then we have a vertical compression. And if a is less than 0, or if it's negative, then we have a reflection in the x-axis. Okay, and that's it for this video. If you have any questions, let us know in the comments below or at lulumath.com, where you can also find blank or completed notes for this video. If you found this video to be useful, please make sure to share with others and please subscribe. Thank you, and we'll catch you next time. Bye.